lecture today. Of course, today we're going to continue from continuous probability distributions, just like what we did under discrete probability distributions, where we're visiting. We started going. We started from Bernoulli to binomial to negative binomial, hypergeometric, and the like. We're also going to do the same under continuous type probability distribution. So today, the focus is going to be on uniform and normal distributions. Okay, so just like what I've been doing, I believe I'm going to commit my class on Friday, the lab, to you know, walking you through examples on this. But what is going to play out today is walking you through theoretical development of these two. Okay, so in the outline, like I said, I'm going to focus on both uniform and normal. Okay, so let's get started. You know, uh, Under a discrete type probability distribution, I walk you through a discrete uniform, right? We also have a continuous uniform. So what is the difference between the discrete uniform and continuous uniform? The discrete uniform, if you take a look at the state space in the discrete uniform, we're actually going to start from one and all the way to a certain number. And of course, the probability of occurrence, okay, is actually going to be equal for all events, so which is going to be maybe 1 over n. But in the case of continuous uniform, we actually are going to be looking at the intervals. Okay. Now, when we identify intervals, maybe intervals A and B, okay, we believe that the probability of the occurrence of a random variable within the interval is actually going to be equal to 1 over B minus A. That you can actually see here. Okay, so this is the probability distribution for continuous uniform. So, of course, we are taking values, let's take values within the interval A and B. Like I said, it doesn't really matter whether it is close at both end or open at one end, close at one end, or they are both open. So it's actually all the same. Okay, so just like every other probability distribution, we can actually derive the mean and the variance. Okay, the mean and the variance is actually this is the mean, this is the variance. Okay, which I'm gonna also walk you through. So, here, if x follow uh, uniform, okay, with parameter AB, okay, of course, we know that f of s is 1 over b minus a, and where s lie between a and b. So if I want to find expected value of s, so here I'm actually going to have x f of x ds, for all continuous probability distribution. If I want to find expected value of x, this is what I'm going to do. So a to b, okay, x 1 over b minus a ds. So 1 over b minus a, so a to b, x ds. Okay, so if you take a look at that guy now, so you actually 1 over b minus a, so s squared over 2 ba, so 1 over b minus a, so b minus a all squared divided by so if you, because you're gonna be plugging in, you're gonna plug in b's, so you're gonna plug in a. Okay, so this guy is b minus a, B plus A, mathematically speaking. So you have that guy, and of course, that was how we actually derive the mean, okay, to be equal to that. So you can try variance on your own, okay, but I'm going to give you a clue, okay, for the variance. You're still going to use what we've been using. Of course, right now, you don't know this guy, but you know B plus A over 2 or squared. So you can also find this S squared using this F of S, ds, A to B. So A to B, okay, S squared 1 over B minus A, okay, ds. So if you finish this up, okay, yourself, and if you use the formula for variance, okay, you actually gonna have B minus A all squared divided by 12. Okay, if you can, if you follow all of that. So based on what we've been doing, you're actually gonna derive that. So the essence of this distribution, the fact that you hear uniform. Okay, so for instance, if I come to a random person in this class and I ask about the day the person is going to be celebrating his birthday, of course, it's going to lie between day number 1 to day number 365. So which is going to be 1 over 365. Okay, so it's going to be equally likely. So it's going to be equally likely the person is going to have his birthday in a particular day within the year. And we use this distribution in computer simulation. Like I want to simulate numbers, okay, they're over a range of A to B, okay. The idea of using uniform is to guarantee what I call equal chance to numbers within the given, interval. Okay, so this about uniform. Is there any question on this uniform? Do you know? I can ask you to derive the moment generating function, okay, for this distribution, okay, ms of t, don't forget, expected value of e raised to power ts, okay, integral e raised to power tx, f of s, dx, a to b, okay, so I'm going to leave you to finish it up. Okay, this minus d ds, so finally you're actually going to have etb minus eta over t into b minus a, okay, in the end, that's what you're going to have. So b, a, and b minus a, and x of t, okay, so you can also use the moment generating function to derive the mean and the variance, okay. So a lot of questions can actually be asked. Okay, so that is that. Like on Friday where we're doing the lab, now I'm going to walk you through how do we compute all of this. You can see a uniform 2, 7. It means your A is 2, your B is 7. Distribution. You can actually figure out what does it mean here? What is the standard deviation? That's going to be super cool, right?